Yes, hello, grade 11s. How are you today? My name is Patrick Kamala. I am a tutor and educator for mathematics and physical sciences, grades 10 to 12. Today, I want us to go through the scope for your upcoming test for the end of year 2022. Now, we're going to use the following. This is the sheet we're going to use for the formulae, okay? And also you're going to use the periodic table as we proceed. Now today we're talking about the quantitative aspects of a chemical change. We're talking about quantitative aspects of a chemical change. So we have the important terms in here. One of them is called the mole. And what is the mole? The mole of a substance having the same number of particles as there are atoms in 12 grams of carbon-12, and then that's called the Avogadro's number, the number of particles or atoms, molecules, formulations present in 1 mole, and then molar mass, the mass of 1 mole of a substance that measured in gram per mole. And Avogadro's law, 1 mole of any gas occupies the same volume at the same temperature and pressure. And then lastly, concentration, the amount of solute per liter of solution. Now, this was just the introduction. Let us go into the exact stuff which we are looking for. Now, today we are talking about the quantitative aspects of a chemical change. We're talking about what? Quantitative aspects of a chemical change. Yes, hello. Now, quantitative aspects of a chemical change. To start with is the mole. It is the mole. What is a mole? Now, let us start from here. Now, I want you to understand that atoms, molecules and ions are too small to count, and there are so many particles in even the smallest sample of a substance. There are, for example, there are more particles of water in a teaspoon, that's 1 spoon, than there are teaspoons of water in all the oceans. Can you imagine that if you get a spoon of water and analyze all the particles on that spoon of water, it's more than the number of teaspoons of water in all the oceans altogether. So rather than dealing with the particles individually, we deal with a special number of particles. And so we talk about the mole. Now, the mole is a name for a special number, okay? And many numbers have names, okay, such as 2 standing for pair, 3 hat trick, 12 dozen. So like you see, a pair meaning 2, dozen 12, okay. Likewise, the mole is the SI unit, okay. It is what? It's the SI unit which we use to show amount of a substance. So the mole is the SI unit for the amount of the substance. Now, what is a mole actually? A mole of particles is the amount of 6,02 exponent 23 particles. So if anybody talks about mole, you must understand it is simply an amount of particles, okay, which is as much as 6,02 times 10 to the power 23 particles, okay. Now, the 6,02 times 10 to the power 23 is called the Avogadro's number, which we abbreviate as Na. So whenever you see Na, we mean Avogadro's number. Now, Avogadro's number is a very large number to imagine. It is actually 6,000,000,000,000,000,000,000,000,000,000,000,000,000. So it's such a big number. For example, this many grains of sand piled on the surface of the earth would almost reach the moon. So the mole is defined as the number of particles or atoms in 12 grams of carbon-12. Okay, so you can also say that the mole is defined as the number of particles, all atoms in 12 grams of carbon 12. Are we together? That was the mole. So you can say a mole of particles is an amount of this 6,02 times 10 to the power 23 particles, or you can say that the mole is defined as the number of particles, all atoms in 12 grams of carbon 12. Are we together? Let us proceed. What about molar mass? What about molar mass? Particles are too small to weigh individually, so molar mass M is defined as the mass in grams of 1 mole of particles. These particles could be atoms, molecules, or formula units, and is measured in what? In unit grams per mole. Okay. Now the number of moles is given by the formula N equals to mass over molar mass, whereby M is the mass of the substance in grams, and the capital M is molar mass in grams per mole. Then from molar mass, another term is called relative atomic mass. That's AR, is the average mass of an atom compared to the mass of a carbon-12 atom. It is measured in atomic mass units. Okay, so if we say define relative atomic mass, you say the average mass of an atom compared to the mass of a carbon-12 atom, and it is measured in what? Atomic mass units. Okay. Now the molar mass M of an element is equal to the magnitude of relative atomic mass of that element in atomic mass units. So this is found in the periodic table, and we have some substances to show you here below. Okay. We have got the type of substance, the particles, and example. Okay. Now, for example, the elements we have got, they contain atoms. For example, neon, the formula is Ne. The molar mass is 20 grams per mole, meaning 1 mole weighs 20 grams. And then covalent compounds, they usually contain molecules. For example, carbon dioxide, that is CO2. To get the molar mass, we add the mass for carbon, that's 12. Then oxygen, these are 2 oxygen atoms, so I'm going to say 16 plus 16, which gives me a total of 44. And then if it comes to ionic compounds, we have ions, the formula units. For example, these are salts like sodium chloride. Now to get molar mass, again, we add for sodium, which is 23, and then chlorine, which is 35,5, giving us what? 58,5. And then lastly, we have what we call as metallic compound. They contain positive kernels and localized electrons. For example, gold, which is Au, has a molar mass of 195 grams per mole. Hope we add together. Let's look at some examples here that you get this properly. Now, what is the relative formula mass of calcium sulfate? That is CaSO4. Now, calcium itself has got a mass of 40. What about sulfur? It has got a mass of 32. What about O? That is 16. But because of the we're gonna say 16 times 4. So when we add 40 for calcium, 32 for the sulfur, and the 4 times 16 for the O4, then we get what? We get 136. Now, because the question was about the relative formula mass, we don't have a unit here. But however, if the question says what's the molar mass of calcium sulfate, then it's the same as this 136, but it must be measured in what? In grams per mole. Hope we are together. Let us proceed. I'm sure by the end of this video you'll be fine with the quantitative aspects of the chemical change. Just sit back and listen and watch. Okay. Now let us talk about what we call as the percentage composition. That means percent of an element. What we do, we get the total mass of elements in a compound divided by the molar mass of the compound times 100. For example, consider these iron ores, that is hematite and magnetite, which contain more iron by mass. The ore, we have the hematite and the magnetite. The formula for hematite is Fe2O3. What about magnetite is what? It is Fe3O4. So we get the relative molecular mass of each. For iron, it's going to be 2 times 56. What about oxygen? Going to be 3 times 6, which gives us 160. What about here? We see it gives us what? 232. Okay. Now, if you check the percentage of iron, now this one here, it is for iron. This is for iron here. Let me underline it. So for iron, as you can see, it is 2 times 56. Ne? Are we together? And then that is in the hematite, which is 112. Okay. And then what about for magnetite? It is 3 times 56. Okay. So what we do, we divide this one over 160 then times 100, which gives us 70%, which means hematite contains 70% of the iron by mass. Okay. And then magnetite contains what? 72% of iron by mass. So our answer could be what? Magnetite contains more iron. Don't forget the question was saying that which one contains more iron by mass. So it is magnetite, this one here, because I've got 72, which is higher than the 70%. Now we have other different types of chemical formulae which we use in chemistry, and they include the following. This is a ball and stick model of the ethane. This C is carbon, another carbon. These are hydrogens here. Okay, these gray, they are hydrogens. Now it also can be represented using a formula. There are 3 types of formulas which we use here. We have a molecular formula. That one shows the actual number of each atom. For example, C2H6. Now we can have what we call the empirical formula, which shows the simplest whole number ratio of the atoms. For example, from here, if I divide by 2, I'm going to get C1 and H3, okay, which we write as CH3. So this is the empirical formula for this molecular formula. And then we can also show the structural formula and show the bonds, okay, like you saw. This carbon is what you saw here. That's the black which you see here, and then this hydrogen, that is 1, 2, 3. That's what you see, 1, 2, 3. And then this other carbon is this other black one here also, and then 1, 2, 3. These are the hydrogens, 1, 2, 3. So here we show the structural formula. Okay. Now another example here also could be, what is the relative molecular mass of sucrose? That is C12H22O11. Okay. Now we're going to do it. Carbon is 12, so we're going to say 12 times 12. Okay. What about hydrogen? It has got mass of 1. It's going to be now 1 times, what's there? 20, going to be 1 times 22. What about oxygen with 11 of them? It's going to be 11 times, which gives us what? 342. Because this is relative molecular mass, it has no units. Okay. However, if the question said what's the molar mass of sucrose, it would be the same value, but with this time we say grams per mole. Hope we are still together. Let us proceed, guys. Next, let's look at concentrations of solutions. Concentration of solutions. Concentration. Okay. Now solutions are homogeneous or uniform mixtures of solute and solvent. The solvent and the solute can be a gas, liquid, or solid. The most common solvent is liquid water. This is called aqueous solution. Okay, so whenever you see aqueous solution, you mean something has been dissolved in water. Where we have a solution, solute, and solvent. For example, salt water, it contains a salt, and that's a solute, and then the solvent is water. And then soda water, the solute is carbon dioxide. What about the solvent? Is also still water. Now, what is concentration? The concentration of a solution is the number of moles of a solute per unit volume of solution. They can say, define the term concentration. In your exam, you say that the concentration of a solution is the number of mole of solutes per unit volume of the solution. Okay, now we have got many formulas to get concentration. This is one of them. We can use concentration C in moles per decimeter cubed as C equals to N over V, whereby N stands for the number of moles. What about V? Volume, but it must be in decimeters cubed. And you can also get it using the formula C equals to mass over molar mass times V. So in this case, the number of moles of solute per 1 decimeter cubed of a solution, that's a mole per decimeter cubed. If a solution of potassium permanganate, for example, has a concentration of 2 moles per decimeter cubed, it means that for every 1 decimeter cubed of solution, there are 2 moles of potassium permanganate dissolved in the solvent. Note this for our calculations, that 1,000 cubic centimeters same as 1 cubic decimeter, which is same as 1 liter, and then 1 cubic centimeter same as 0.001 decimeters cubed, and then what about also the same as 1 milliliter. Some examples to do here so that you understand this much better. A solution contains 10 grams of sodium hydroxide in 200 cubic centimeters of solution. Calculate the concentration of the solution. Remember, they have given us what? They have given us the mass of sodium hydroxide. That's our solute. Okay? And then they're saying that it is sodium hydroxide in which volume? In 200 cubic centimeters. Okay? So we need the concentration. So now, because you said C equals to N over V, it's better to first get the N, which is the number of moles given by mass over molar mass like this. The mass given is 10 grams. Then molar mass of sodium hydroxide is going to be what? 23 plus 16 plus 1, which gives us 0.25 moles. After getting our moles, then the given volume must be decimeters cubed. So what do? Divide by 1,000 to get what? 0.2. So mean that now our concentration equals to number of moles divided by volume, which gives us what? 0.25 by 0.2, which gives us 1.25 moles per decimeter cubed. Hope we are together. Another example here is calculate the mass of solute in 600 cubic centimeters of 1.5 moles per decimeter cubed sodium chloride solution. Now this time what do they want? They say calculate the mass. We are looking for the mass of the solute, okay? In which volume? In 600 cubic centimeters. And what about they give us a concentration of 1.5 mole per decimeter cubed? Okay, sodium chloride solution. So we're looking for the mass. So the volume given must be converted to decimeters cubed first, which gives 0.6, and then we get the molar mass of sodium chloride, which is 23 plus this to give us 58.5 grams per mole. Then we know that our number of moles equals to CV. Why? Because we have said that that C equals to N over V. Do you remember that? We have said C equals to what? Concentration C equals to N over V. So which means if I'm looking for the number of moles, I just make it N. It's going to be N equals to CV. Okay, that's why we have here what? That's why I have N equals to CV. Now C is for the concentration, that is 1.5. What about the V? It is this one here, which is 0.6. So I get 0.9. After getting moles, the question wants the mass. But I also know the formula says that number of moles equals to mass over molar mass, which means that if I'm looking for the mass, then I can say that don't forget we have said that number of moles is the same as what? Mass over molar mass. So mean that if I'm looking for this mass, I will have it as mass equals to number of moles times molar mass. That's what I'm doing here exactly. So because I have the moles 0.9 here and I know the molar mass 58.5, so I have to multiply to get what? To get my mass, which is indeed here as what? As 52.65 grams. Hope we are together. Okay, let us proceed. That was calculating the mass given concentration. This one was calculating the concentration given the mass and the volume. Okay, now not something so special with gases here. Now the molar volumes of gases, in different gases, if different gases have the same volume, under the same conditions of temperature and pressure, they will have the same number of molecules. Okay, now check these 3 different types of gases. You see these containers are equal in volume. Okay, they're equal in volume. So because the containers are equal in volume with the same under the same pressure, so different gases will contain the same number of moles. Are we together? So check here. This is one atom, one atom. This is 1, 2, 3, 4, 5, 6. These are 6 moles. Check here. 1, 2, 3, 4, 5, 6. Oh, these are also 6. Check here now. 1, 2, 3, 4, 5, 6. These are also 6 moles. So now, as long as the volume is the same, are we together? And the temperature and the pressure for any gas, they all have what we call as what? The same volume. And for that case, if you get something standard, then we come up with what we call as what? The molar volume of a gas. Okay? Occupied by 1 mole at STP. So in this particular case, understand, guys, that the molar volume of a gas, that is V molar, is the volume occupied by 1 mole of the gas. Did you hear that? We're saying that the molar volume of a gas, Vm, is the volume occupied by 1 mole of the gas. Okay. Now, the Vm for all gases, whether be it oxygen, nitrogen, hydrogen, any gas, as long as it is at STP, it is 22.4 decimeters cubed per mole. We are going to see this so much in our calculations shortly to come. Please, you can keep it in your head, or you can always refer to the formula sheet, the data sheet, which contains 22.4 decimeters cubed per mole. Now, what is STP? We mean the standard temperature and the pressure, whereby temperature is 273 Kelvin or 0 degrees Celsius. What about the pressure? It is 1,013 exponent 5 pascals or 1 atmosphere. Okay, now this also means that because they contain the same number of moles at STP, all the gases, it means that for a reaction at constant temperature and pressure, the gas volumes react in the same ratio as the molar ratio. Did you hear that? The gas volumes react in the same ratio as what? As the molar ratio. Are we together? For example, if this is nitrogen plus oxygen to give me nitrogen dioxide, you see here this is 1, okay, plus 2 to give me 2. So now we see here, because of this one here, it means that actually 1 mole of nitrogen reacts with 2 moles of oxygen to give me 2 moles of nitrogen dioxide. But if I talk about only volumes now, again, it means 1 decimeter cubed of nitrogen reacts with 2 decimeters cubed to give me what? 2 decimeters cubed of nitrogen dioxide, because moles and the volumes, they are the same if it comes to relation with gases. Okay, now because all the gases have the same molar mass at STP, then we have this formula now modified. Now, number of moles equals to volume divided by V molar, whereby volume of the gas of the substance given must be what? Decimeters cubed. What about the V molar? It's a standard. We said its value is what? It is 22.4 decimeters cubed per mole. Hope we are together. We're going to use in our calculations. For example, here they say that what? They say a gas jar with a volume of 224 centimeters is full of chlorine gas at STP. How many moles of chlorine gas are there in the gas jar? I repeat, the question says that a gas jar with a volume of 224 centimeters is full of chlorine gas, not at STP. Then they say how many moles of chlorine gas are there in the gas jar. So because I know this formula here, N equals to V over V molar, I'm gonna say N equals to V over V molar. And because I want how many moles, I'm gonna, now the given volume here, it is what? 224, but I must convert it from cubic centimeters to decimeters cubed. What do? I divide by 1,000, which gives me 0.224. Now divide by the what? By the standard volume of V mole at 22.4, which gives me what? 0.01 moles. Are we together? Hope we are still together. Let's proceed, guys. And then apart from that, we'll talk about what we call as water of crystallization. Okay. water of crystallization. Water of what? Crystallization. Now please understand also that some ion crystals trap a certain number of water molecules between the ions as they are forming. So these water molecules are known as water of crystallization. For example, hydrated copper sulfate. Now we write it as copper sulfate dot 5 water. Now it has 5 water molecules per formula unit. When the hydrated salt crystals are heated, the water molecules evaporate off, leaving the anhydrous salt behind. For example, if I heat this copper 2 sulfate 5 water solid crystal, I'm going to get one which doesn't have water, which is not hydrated now. That's copper 2 sulfate solid plus the 5 water. Okay, this one has been given off now. Okay, remember it was containing water of crystallization here. Now it doesn't contain anymore because it has been boiled off, all burnt off, all heated off. Hallelujah. Are we together? Then now to calculate the number of moles of water of crystallization, we have got a steps which we follow. Number one, what do? You calculate the mass of the water that evaporated off, and then calculate the moles of water, then calculate the moles of the anhydrous salt, then determine the ratio of the water to anhydrous salt, then write the formula for the hydrated salt. Note something, that the dot in the formula between the salt and the water means that a light bond is formed. It is not a multiplication dot. Okay, so then let us have an example here. For example, here we said that 13.2 grams sample of zinc sulfate was heated in a crucible. Calculate the number of moles of water of crystallization if 7.4 grams of solid remained. Okay, so check here that we have what remained, that is 7.4 grams. This one was containing water of crystallization. That's why it is X water here. So the question says calculate the number of moles of water of crystallization if 7.4 grams of the solid remained. So now this is the mass of the water. It's going to be the difference in the mass. That means 13.2 minus 7.4, which leaves you with what? 5.8 grams. What about the number of moles of water? It's going to be mass over molar mass. This 5.8 divided by what? By 18, which gives us what? 0.32 moles. And now the zinc sulfate which remained, it was 7.4. So I divided by the molar mass of zinc sulfate, which is 161 from periodic table, and then I get 0.046 moles. So to get how many moles of, to get the water of crystallization, I'm going to say this 0.32 from the water divided by 0.046. Then I'm going to get the ratio as what? As 1 to 7. So meaning that the formula zinc sulfate contains 70 water molecules of crystallization. Hope we are together. If not, don't worry, we have another example shortly coming soon. Okay, now let us talk about something to do with the empirical formula from percentage composition. The empirical formula of a compound can also be found from its percentage composition. We assume that 100 grams of the compound is analyzed, then each percentage gives the mass of the element in grams in 100 grams of the compound. Okay, for example, an oxide of sulfur contains 40% sulfur and 60% oxygen by mass. Determine the empirical formula of this oxide of sulfur. Don't forget it contains what? 40% sulfur. What about oxygen? 60%. So what we do here, we have got sulfur and then oxygen. So if you look at our percentages here, sulfur it is 40, oxygen is 60 here. Then you get the mass of each element. Sulfur it is, that's what we have here, 40 and 60. And then now the moles, we divide mass by molar mass, which gives us 1.25 for sulfur. What about oxygen? It gives us 3.75 after dividing 60 by 16. So now if I check here, 1.25 and 3.75, which one is the smallest? It is 1.25. So on the next step, please divide by the one which is smallest. Okay, so you're going to divide by 1.25 here and this side, which gives us here 1. Then you have 3. Now mean that our empirical formula is going to be 1 sulfur and then 3 oxygen. That's why it is sulfur trioxide. That's our empirical formula. Are we together? Now, what is empirical formula actually? They can say to define it. Or the empirical formula is the chemical formula of a compound that shows the smallest whole number ratio of the atoms. They can say define empirical formula. What will you say? Empirical formula is the chemical formula of a compound that shows the smallest whole number ratio of the atoms. Hope we are together. Okay. Let us look at some more examples here to make this more understandable. Here. Okay. Now, a sample of oxide of copper contains 8 grams of copper combined with 1 gram of oxygen. Find the empirical formula of the compound. So here we have the masses now. 8 grams of copper and 1 gram of oxygen. So what the steps we have? Copper and then oxygen here. Copper, the mass is 8 grams. What about oxygen? They said 1 gram. So we're going to get the number of moles. That means 8 divided by 63,5 on the side of copper, which gives 0,126. What about oxygen? It's going to be 1 divided by 16, which gives us 0,0625. And then after, now check it on the smallest here. It is 0,0625. So divided by this one, both sides here, I'm going to get 1. What about it? It's going to be roughly 2. So in this case, our copper 1 oxide is going to be like this. It's going to be Cu2 then O. So that's our empirical formula, which is Cu2O. Hope we are together. Are we together? If you're not together, please, you can contact us on this number for more clarity. Okay. However, let us proceed. Next here, we talk about empirical formula again to molecular formula, how they are related. Okay. Now, the empirical formula is the simplest whole number ratio of atoms in a molecule. Okay, we said that before, just to make it more clearer to all of us here. We're saying that empirical formula, it is the simplest whole number ratio of atoms in a molecule. Okay. Now, the molecular formula is the actual ratio of the atoms in a molecule. That's how they differ. I repeat, empirical formula, it shows or is the simplest whole number ratio of atoms in a molecule. What about now molecular formula, teacher? Then molecular formula is the actual ratio of the atoms in a molecule. So the actual ratio of atoms in a molecule is called molecular formula, while the simplest whole number ratio of atoms in a molecule is called empirical formula. Now, the molecular formula can be calculated from the empirical formula and the relative molecular mass. Okay, these are the steps to determine the molecular formula. First, determine the empirical formula if not given, then determine the molar mass of the empirical formula, and then determine the ratio between molecular formula and empirical formula. Then multiply the ratio into the empirical formula. Then there you go, you'll be fine. Example, butene has the empirical formula CH2. The molecular mass of butene is 56 grams per mole. Determine the molecular formula of butene. They're saying this is the empirical formula, that is CH2. Then the molecular mass of butene is 56. Okay. Now they want molecular formula of butene. So empirical formula given to us is CH2. What about the what? The molar mass for CH2 is going to be 12 for carbon. But now these are two hydrogens, it's going to be 1 plus 1, which gives us what, 14 grams per mole. Now if I look at the ratio number between the molecular formula mass and empirical formula mass, now here they gave me 56, so you see it. So I'm going to say molecular formula divided by empirical formula, which means 56 over 14 giving us 4. So in other words, we can say that our molecular formula is going to be given by C4H8. Are we together? However, there is some method which is simpler than this here. We could also have said like this. Okay, we can say like this here. Pay attention, please. I can say that molecular formula Okay, molecular formula equals to N divided by what? Multiplied by the empirical formula. So in this particular case, to get my molecular formula, I'm going to use the molar mass given to me, which was 56. That's 56 there. 56. Okay. Equals to N. Okay. What's our empirical formula? This is C and H2. Now C has got how many grams? That is 12. Okay, 12. What about H2? That's 2. Okay, and in this case I'm going to have 56. Okay, equals to what? What is 2 plus 12? It's going to be 14N. 14N. Okay, 14N. So divided by 14. Divided by 14. So if after dividing by 14, I'm going to get my N to be what? Calculators, what do you get? I get 4. Okay. Now after getting 4, then to get my molecular formula, I just said that molecular formula, okay, equals to N, open brackets, empirical formula, which was what? Which was given by C1H2. Okay. Then now I multiply through by N, but my N is 4, right? So if I open brackets here, I'm going to have the molecular formula direct. Okay. So what is 4 times 1 here? I'm going to get C4. Okay. What about 4 times 2? I'm going to get H8, which means this is my molecular formula now. Okay. Hope we are together. So that's another method of doing this. Okay. Alright, let us proceed. Let us proceed here. Now we use balanced chemical equations. For example, nitrogen gas plus hydrogen gas to give us 2 ammonia. The balanced chemical equation is the recipe. It tells us the reactants used, nitrogen and hydrogen, products produced, that's ammonia. The states of the reactants and the products, that's all gases here. The molar ratio of the reactants to products. For example, 1 molecule of nitrogen reacts with 3 molecules of hydrogen to form 2 molecules of ammonia. Then 1 mole of nitrogen reacts with 3 moles of hydrogen to form 2 moles of ammonia. Let us check what is happening here. Now after knowing that empirical formula and the molecular, we can also look at what we call as stoichiometry, how to write a balanced chemical equation, then change the given amount into mole, then using limiting reactant if applicable, and also determine the number of moles of the asked substance using the mole ratio, and then determine the asked amount from the number of moles. So this is the procedure which we follow here. For example, to obtain iron 3 oxide reacts with carbon monoxide according to the following word equation. That's to say iron 3 oxide plus carbon monoxide giving us iron plus carbon dioxide. The question says what mass of iron is produced from 48 grams of iron 3 oxide. I repeat, the question says that to obtain iron 3 oxide reacts with carbon monoxide. So we have got iron 3 oxide as one of the reactants with what? With carbon monoxide. With carbon monoxide according to the following equation here. This is the equation here. This is the equation here. Now the question says that what mass of iron is produced from 48 grams of iron 3 oxide. So after writing our equation like this and then balancing it, then we can proceed like this. The question is what mass of iron is produced from 48 grams of iron 3 oxide. So because we have the 48 grams of iron 3 oxide, it means we can get the moles of iron 3 oxide first by saying moles equals to mass over molar mass, which gives us 48. This 48 divided by the molar mass, which is 1, we get 0.3. And then look at the mole ratio of iron 3 oxide together with what we are looking for, that is iron. So here it is 1 is to 2, meaning this is 1 to 2. Now this 0.3 they are for iron dioxide, which that's why we're putting it here. And then because it's 1 to 2, it means it's going to be multiplied by what? By 2 to give us 0.6 moles. After getting the moles of iron, then 0.6, what do? I'm looking for the mass, so I know that mass equals to moles times molar mass, okay? Because we said that number of moles equals to mass over molar mass. So if you make M, the subject of the formula gives you M equals to N times molar mass, which gives us 33.6 grams. Okay, now we have got steps which we follow here, follow the procedure to do this. First of all, the given the step 2, we have the given value converted to given moles, then from given moles to asked moles, then from asked moles to asked value which they want, which whether it is in grams or decimeter or centimeters cubed. Then we follow these steps here. For example, here now note something, guys, here that after that in my equation, which is balanced, I have to find the number of moles, which I can get by using moles equals to mass over molar mass. All moles equals to C times V. What is C? Concentration. V the volume in decimeters cubed. Or I can use N equals to V over V molar. We said it's 22.4 at STP. Are we together? Then from there, now after getting these moles, now I use the mole ratios to convert the given moles to asked moles using mole ratios. Are we together? After getting mole ratios, then in step 4, now I can either, if they calculate the mass, I can say that mass equals to N times molar mass, or I can say now that my concentration is going to be moles divided by volume, or I can say volume equals to moles times 22.4. as we're going to see in the examples to come shortly. Hope we are still together. Are we together, guys? If you're not together, please, you can inbox me on 0785, or you can come to our tuition center in Pulukwane here, Rose College 92 Schoolman. Okay, another important part is limiting reactants here. They say in a reaction between two substances, one reactant is likely to be used up completely before the other. This limits the amount of product formed. Consider the reaction between magnesium and the sulfuric acid. The balanced chemical equation is this one: magnesium sulfate plus sulfuric acid to give us magnesium sulfate plus hydrogen gas. This means that 1 mole of magnesium reacts with the 1 mole of sulfuric acid. Both reactants will be completely used up by time the reaction stops. That's if I've got 1 mole and 1 mole, they will both be completely used up at the end of reaction. Now, what happens if 1 mole of magnesium is and the 2 moles of sulfuric acid are available to react? So if I've got 2 moles of sulfuric acid, then with 1 mole of magnesium, now note that there is now insufficient magnesium to react with all of the sulfuric acid. So it means that 1 mole of sulfuric acid is left after the reaction. So for that matter, all of the magnesium is used up. Then we say that magnesium is the limiting reactant. In other words, if they say what is a limiting reactant, what will you say? It is a substance which is completely used up. And then some sulfuric acid is left after reaction. We say it's what? It is in excess. Okay. Now the amount of limiting reactant will determine the amount of product formed. Are we together? Also determine the amount of other excess reactants used. Now if I want to get limiting reactants, we have got some steps to follow here. Step number 1, calculate the number of moles of each reactant. Step number 2, determine the ratio between the reactants, and then determine the limiting reactant using those ratios. So we're going to look at the examples. Note, if one reactant is in excess, it means that there are more than enough of it. If there are only 2 reactants and one is in excess, it means that the other is the limiting reactant. Did you hear that? If there are only 2 reactants and the one is in excess, it means what? The other is the limiting reactant. Hope we are together. Let us proceed. For example here, they say that 8.4 grams sample of nitrogen. Okay, let's take it properly. We are saying that okay, example here, the question says that 8,4 gram sample of nitrogen reacts with 1,5 gram hydrogen. The balanced equation is here. Nitrogen plus 3 hydrogen to give us 2 ammonia. What's our mole ratio here, guys? 1 to 3 to 2. Okay. The question says, determine which reactant is the limiting reactant and then the mass of ammonia that can be produced. I repeat, please understand the question. We are saying that 8,4 gram sample of nitrogen reacts with what? 1,5 grams of hydrogen. Okay, so I'm reacting nitrogen and hydrogen. As you see them here, I have the mass for each one of them. The question says, determine which reactant is the limiting reactant. Okay. Let us look at what we need here. Now, first of all, we are going to convert the given masses to moles. And we know that moles equals to mass over molar mass. So with nitrogen, it is 8,4 divided by 28 because it is 14 times 2, which is 28 here. I get 0,3 moles. Are we together? What about hydrogen? Because it is H2, I'm going to have the mass 1,5 divided by 2. 2 coming from 1 times 2 because 1 is the molar mass for hydrogen. Because there are 2, going to be 2 here. So divide here, it gives me what? 0,75 moles. Okay. Now we are going to decide which of the 2 is limiting. Are we together? This is 0,3. This is 0,75. Okay. What was our mole ratio again? Nitrogen to hydrogen, it is 1 to 3. 1 to what? 1 to 3. Let us proceed then. So, if I look at my mole ratio, 1 to 3, I have, these are the available moles. 0,3 moles of nitrogen. Because it's 1 to 3, it means the one I'm going to need for hydrogen is going to be what? It's going to be this one multiplied by 3, which is 0,9 moles. But however, I only have 0,75 moles available. So what do you think, guys? Talk to me. Look here. I need 0,9 moles, okay, of hydrogen to completely react with what? With all 0,3 moles of nitrogen. But I only have 0,75 moles. So talk to me. What do you think is the limiting reagent here? Now, because this one is not enough, it's less than 0,9, it means that hydrogen is my limiting reagent. And so for that matter, the 0,75 that I have available will only consume 0,25 of the nitrogen. So nitrogen is not in excess. Are we together? So this is 0,75. The ratio is 3 here. Now you can say, how do you get this one? 0,25 by dividing 0,75 by 3. I get what? I get 0,25, which I need for nitrogen because mole ratio was 1 to 3. Okay, so now for that matter, hope we are together. Now we say here, if all nitrogen is used, 0,9 mole hydrogen is needed. However, only 0,75 moles of hydrogen is available. So the hydrogen will run out first. Therefore, hydrogen is the limiting reactant. Hope we are together. And because the hydrogen is the limiting reactant, it will determine the mass of ammonia produced. So if you look at our equation again, the mole ratio of hydrogen to the ammonia is 3 to 2. Let's check it once again. 3 to 2. How do we get it? We get it from here, guys. This is 3 to 2. So because this hydrogen is a limiting reactant, I must use hydrogen and then ammonia ratios to get what's going to be produced. Somebody can say, why don't you use one which is in excess? Because it will be misleading. I don't have enough hydrogen. Okay, did you hear that? I don't have enough hydrogen. So I must use hydrogen to know how much ammonia I can produce. Because as soon as hydrogen gets finished, it means the reaction will stop because I don't have any more of it. Remember that nitrogen was in excess. Okay, let us proceed. So we have said that because hydrogen is the limiting reactant, it will determine the mass of ammonia produced. That means hydrogen to ammonia is 3 to 2. we see that because this is 3 to 2 and I have 0.75 moles of hydrogen, it means I can get 0.5 here. How do you get it? Let me show you a shortcut again here. Assume I don't know the 0.5 here. Let me put x here. If I put x here, what can I do to get my x? This is what we do. Now if I have got x here instead, and I don't know this answer, I don't know this answer here, what I do, I'm going to cross multiply. I'm going to say 3 times x, cross multiply this 3 with this x here, equals to 2 times 0.75. okay, look here, because I'm going to say 3 times x, that is 3x, okay, equals to what? Equals to 2 multiplied by what? By 0.75. So because I'm looking for x, I divide by what? I divide by 3. It's going to be 2 multiplied by 0.75 divided by 3. So calculators, you tell that your x is going to be what? It's going to be 0.5 moles, meaning that if I react 0.75 moles of hydrogen, I will indeed get 0.5 moles of the product, which is ammonia. Okay, so after getting moles of ammonia, then I can get the amount of ammonia, because we said that mass equals to moles times molar mass, and so I can get 0.5 times 17, which is giving me 8.5 grams. Hope we are together. Are we together? If you're not together, please, you can inbox me on this number here, or you can come for extra classes at Lost Tech College in Pulkwani here. Now we have also what we call as percentage purity. Sometimes chemicals are known pure, and one needs to calculate the percentage purity. Only the pure component of the substance will react for an impure sample of a substance. Okay, this is a formula here. Percentage purity equals to mass of pure substance over mass of impure substance times 100. Okay, those are the steps which we follow. First of all, determine the moles of the products. From the balanced formula, determine the ratio between reactants and products. Then, using the ratio, determine the number of moles of reactants. Then, determine the mass of the pure reactant, and then go ahead and calculate your percentage purity of the sample. For example, here, an impure sample of calcium carbonate contains calcium sulfate as an impurity. When excess hydrochloric acid was added to 6 grams of the sample, 1200 cubic centimeters of gas was produced. Measured at STP, calculate the percentage purity of the calcium carbonate sample. The question is given below. I repeat, the question says that an impure sample of calcium carbonate contains calcium sulfate as an impurity. So when excess hydrochloric acid was added to 6 grams sample, then what happened? 1200 cubic centimeters of the gas was produced. Okay, and then that is at STP. Okay, and then they say that go ahead and calculate the percentage purity of the calcium carbonate sample. So look at here, calcium carbonate plus hydrochloric acid gives me what? Calcium chloride plus water plus carbon dioxide gas. Now that I have the volume given for the gas, I can go ahead to get the number of moles of the gas produced. They said that STP, moreover, what did we say, guys? That our number of moles equals to V divided by what? By V molar. So now this 1200 I must divide by 1000. Let's put it decimeters cubed, so it becomes 1,2. So divide by 22,4 to give me 0.054 moles of carbon dioxide gas. Now because I have the moles of the gas produced, it means I can use mole ratio to know the number of moles of calcium carbonate that reacted. So because this is 1 to 1, this is 1 here. Hope you see that. I'm saying there is a 1 here. Okay, and also another 1 here. So mole ratio is 1 to 1. So 1 to 1 means that these moles of the gas formed are the same moles as what? As calcium carbonate which reacted. So because I have now the moles which reacted for calcium carbonate, it means I can go ahead to get the mass of calcium carbonate which reacted by using moles, that is 0.054 times molar mass. molar mass, we saw how to get it already. So it gives us what? 5.4 grams of calcium carbonate. So to get my percentage purity, I use the formula which says that mass of the pure substance divided by mass of the impure times 100. Now, because this is what reacted, it means that's the pure out of all the 6 grams. So I have 5.4 grams divided by 6 times 100, which gives me 90%. So it means the percentage purity of this sample is what? It is 90%. Hope we are together. Let us proceed. Now also we need to know to determine the percentage yield. Sometimes they're going to ask us this in our test, and this is how we get the percentage yield. Now, yield is the measure of the extent of a reaction, generally measured by comparing the amount of product against the amount of product that is possible. So some of the product may be lost due to evaporation into the surrounding air or due to a little being left in the solution. Some of the reactants may not react. So we say that the reaction has not run to completion. So this results in the amount of the product produced being less than the maximum theoretical amount you would expect. So we can express this by the percentage yield. So the formula goes like this: percentage yield equals to actual yield divided by what? Theoretical times 100. Okay. Now, the percentage yield is usually determined using the mass, but can also be gotten from the following. If determined with the moles and the volume, okay, as we shall see in some questions to come ahead. These are the steps which we follow here. Step number 1, determine the moles of the reactants. Step number 2, from the balanced formula, determine the ratio between reactants and the products. Step number 3, using the ratio, determine the number of moles of products. Step 4, determine the theoretical mass of the product. Then step 5, calculate the percentage yield. For example, 128 grams of sulfur dioxide was reacted with oxygen to produce sulfur trioxide. The equation for the reaction is here. That is 2 sulfur dioxide plus oxygen to give us sulfur trioxide. Now they said that if 140 grams of sulfur trioxide was produced in the reaction, calculate the percentage yield of the reaction. So don't forget that the mole ratio is 2 to 1 to 2. And then what did we have at first? We had 120 grams of sulfur dioxide to react with oxygen. Okay, how much was produced actually? It was 140 grams was produced. Okay, now the question wants us to get what? The percentage yield of the reaction. Now, first of all, because we have the mass of sulfur dioxide, we use it to find the number of moles. That means mass over molar mass, that's 120/60, which is 2 moles. Now look at the mole ratio of the sulfur dioxide and then the sulfur trioxide, which we are interested in. So the mole ratio is 2 is to 2. Okay, same as saying 1 to 1 anyway, meaning that then now if we because we have these 2 moles of sulfur dioxide, we are expecting to get 2 moles of sulfur trioxide. So these 2 moles that we are expecting theoretically, we can find the mass which is theoretical by saying mass equals to moles times molar mass. So this 2 times molar mass of sulfur trioxide gives us 160 grams. So for that matter, it means that to get my percentage yield, I'm going to say that mass of product produced, that's what actual, which was 140, divided by theoretical mass, which is 160 times 100, which gives me what? 87.5%. Hope we are together. Are we together? If you're not together, please, you can inbox me here, or you can come to our center for more information. Let us proceed. Now, here I have to say thank you so much for watching. These questions are for you to try because they are part of your scope, and I'm sure if you've been paying attention, you can try them out and then inbox us your answers so that we can mark you before you have your test on Monday. Okay, remember that your final exam contains this scope here. That's why it has been also included here. That is acids and the bases. However, if you want to read about acids and the bases, you can inbox me on my number 0785-222-041 and I can send it to you. However, you can try out these questions here to see if you are ready for your exam on Monday. Are we together? Now we together. The questions continue here. Try them out. I'm sure you'll be perfect by the end of this, and then why not, you can get total. Okay, you can get total. They continue here. They continue. They all include part of your scope. Any challenges, please, you are welcome, inbox me. I'll go ahead and explain to you. Don't forget that at our extra classes, the first 2 days are for free, just to check, as well as the first 2 videos, they're for free, just to check if you like it or not. Okay, so don't feel offended. Just go ahead and inbox us or come to the college, or you can WhatsApp us and get total. Thank you so much for watching. My name again is Patrick Kamala. I'm a tutor and educator here at College in Polokwane. Catch you in my next video. Bye bye.